guys, this is your lesson 20. Today was a little strange, and I learned that we're going to be doing lessons online for the next couple weeks. So wanted to go ahead and get this one out and try and get the other ones out a little early for you if I can. All right, so I will do my best. So we're going to go ahead and start 20. Here we are. So we are studying gas behavior now, and we are wrapping up. We're getting close to the end of our unit on enthalpy, intermolecular forces, states of matter. So for this week, you need to pay very close attention. I'll be throwing up some random images during slides in this lesson, and I mean random, y'all. They're pretty random. You'll know them when you see them. So your job is to post in the discussion in the teacherese assignment and name one of these images, any one of the images you see. Now, we've not used the teacher-led discussion option in teacherese before, so this is new for us, but you should be able to just comment on the thread that I've started. The catch is you can't name anything that someone else has already listed. So be sure that you take note of everything you see. I would write notes as we go so that you don't have to go back and try and find something different. So what's STP? You may recognize that logo, but that's not the STP we're talking about. We're talking about STP, which is standard temperature and pressure, which is 0 degrees Celsius at 1 atmosphere, or 273 Kelvin, or you can also use 101.325 kilopascals or 760 millimeters of mercury. And then we're going to consider a lot of things to be at STP when we're talking about gas laws. So when we're talking about when the pressure of a gas is constant, we move into using Charles's law. And Charles's law states that when the pressure of a gas is constant, if the temperature increases, the volume increases. And if the temperature decreases, the volume decreases. So think about a hot air balloon and how it works. And when you increase the temperature, it inflates that balloon, which increases the volume. And actually, the balloon will float because the number of particles is the same, but the volume has increased, which means the air within the balloon is less dense than the air outside the balloon, which means that the air outside the balloon falls down beneath the balloon and pushes it up. And so Charles's law is what we call directly proportional. Temperature and pressure are directly proportional, meaning if one goes up, the other goes up. If one goes down, the other goes down. So if you were to note temperature and pressure with arrows, they would always be pointing the same direction where Charles's law is concerned. So Charles's law, when we're calculating it, we say that Charles's law calculations involve a change in either temperature, which we would mark as T2, or volume, which we would mark as V2, from a known starting point of V1 and T1. So it would look like this. You have your V1 over T1 equals V2 over T2. V1 and T1 being where we start, V2 and T2 being where we end. And if they're going to be directly proportional, they are going to be multiplied here by a common factor, just like making equivalent fractions. If you think of it that way, it's very, very similar. So what about when we're dealing with the volume of a gas being constant? So now the volume is constant rather than pressure. So then we deal with Gay-Lussac's law. Gay-Lussac's law states that when the volume of gas is constant, if the temperature increases, the pressure increases. If the temperature decreases, the pressure decreases. And here is a good opportunity to think about your Instapot or whatever other pressure cooker you might have as a good example here. So when you turn your Instapot on, you lock that lid. And when you lock that lid, you're keeping that volume constant. It's not like the balloon that can inflate, right? It's a solid structure. It's not going to change. So now your volume is constant, but you're rapidly increasing your temperature, which is causing your pressure to increase. And as long as you don't turn this little knob here on top or whatever analogous feature is on your pressure cooker, then it will not release any pressure. And the increased pressure within the pressure cooker, along with the heat, is what helps cook your food faster. It does that by breaking down the proteins at a faster rate than would normally happen. It's also why pressure cookers have been used sometimes to make bombs. Not this kind of pressure cooker, but the kind that goes on a stove top. It's not electric, and they have locking lids. And the same thing, if you put something in it that's going to explode, you're going to rapidly increase your temperature, and you're going to be forcing the pressure is going to be so strong that it's going to basically force it to break because your volume can no longer stay constant. So, and this is also called Hamilton's law sometimes, but usually you'll hear Gay-Lussac's. So Charles's law or Gay-Lussac's law, temperature and pressure are directly proportional. And directly proportional again, meaning if one goes up, one goes down. If one goes down, the other goes down. If one goes up, the other goes up. So Gay-Lussac's law, calculations using Gay-Lussac's law involve the change in either pressure or temperature from a known starting amount. So again, what we'll see here is our P1T1 and our P2T2, this being the changed amount and this being the starting amount. And again, you would have to multiply directly proportional. In order for it to remain directly proportional, you would be multiplying by a common factor. So when we start talking about the temperature being constant, now when the temperature of a gas is constant, we deal with Boyle's law, which is sometimes called Marriott's law, but most frequently Boyle's law. So Boyle's law says that when the temperature of a gas is constant, if the pressure is increased, the volume decreases. And if the pressure is decreased, the volume increases. So in this case, they're doing opposite things. And a great example of this is taking the lid off of a soda bottle. So when you take the lid off a soda bottle, you are suddenly decreasing the pressure. That lid is keeping the pressure on, right? It's not allowing for any change in volume. And usually if you shake it, you know that there's a lot of pressure building up. So if you take the lid off, you have released the pressure. And we're assuming these are at the same temperature. They're in the same room, okay? So you take the lid off here, and now you've gotten a sudden decrease in pressure. And when you get that sudden decrease in pressure, your volume is going to increase. Now you have the same number of gas particles, CO2 in this case, with the lid on that you do with the lid off. But suddenly what happens is your volume increases, which means that those particles spread out, and now you see them as carbon dioxide bubbles. And they actually can now escape the system if you've removed the lid and opened your system. So Boyle's law says that volume and pressure are inversely proportional. That means if one goes up, the other goes down. If one goes down, the other goes up. So Boyle's law, calculations using Boyle's law involve a change in pressure and volume from known starting points. So in this case, what we have here is a P1 times P and V1 multiplied together equals P2 V2. So if you remember, the others were fractions, so we were dealing with division. In this case, it's multiplication. And this has to do with the fact that they are inversely proportional. So then we have this combined gas law. So if you take Charles's law, Gay-Lussac's law, Boyle's law, and put them together, you end up with what we call the combined gas law. And so if you look, your temperature is always on the bottom, and here it is again on the bottom. And on the top, you have your pressure and volume. So here again, you have pressure and volume. So when you get combined gas law, and in this case, these would of course be on top because you can imagine an imaginary one, right, if you had to have it. So there you have a combined gas law. Now, when we start talking about ideal gas law, it's a little different. So what's the constant? We have to think about this. If you are multiplying this fraction by something to get to this fraction, it's going to be a common number, right? It's going to be a constant. So say your number here is 5 and your number here is 10. You know that you've multiplied by 2. So if you've multiplied by 2, then both top and bottom will go by 2. So if this is 3, then this has to be 6, right? So what we call that constant, we've given it a specific letter. And the letter we've given it is K. So sometimes you will see Charles' law written this way. you'll see V divided by T equals K. Or for Gay-Lussac, you'll see P divided by T equals K. Or PV equals K. Or PV divided by T. So sometimes you'll see K denoted as the constant, and you'll see these laws written this way. So ideal gas law. So this is one I've said before, there are certain things it's helpful to just kind of memorize because you're going to see it again in life, and it's something that a lot of people just kind of know. This is one of them. So PV equals nRT. Ideal gas is a conceptual approximation that helps us model and predict the behavior of a real gas. So it's literally a pretend gas that we use in these functions, in these equations, so that we have something to work with, because all gases are a little different. So in ideal gas, the molecules don't attract or repel each other, and I love this one, they take up no volume. So obviously it is ideal, and it's what we use to work out the problems. So the ideal gas equation, which is this PV equals nRT, and it's a combination of these equations, but it's a little different than the combined gas law. So basically, you've got your P as your pressure, your V as volume, your N is your number of moles. Your R is the ideal or universal gas constant, which is equal to the product of the Boltzmann constant and the Avogadro constant. And then your T is your temperature. And there's a chart for PV equals nRT. So what the heck is R? So this is what I'm saying. Your R, which is your ideal constant. So here is a video, and watch it just not work because I'm in the middle of trying to record this. I may just have to attach this separately, y'all. Okay then. I'm going to attach that one separately. So your ideal gas equation, here are your values of R. So here are some examples. Oops, my face is in your way. Of some values of R. And the video makes more sense of that. So moving on, Gay-Lussac's law of combining volumes. So this one has to do with when gases combine at constant temperature and pressure, the volumes involved are always a ratio of simple whole numbers. So here you see you have 2 hydrogen and 2 hydrogen, and they're combining in a simple whole ratio number. And then your 2 oxygen, and then this is how you're going to get H2O, right? Your ratio would be 2 to 1 to 2. So it's similar to your law of definite proportions, but this law is for volume relationships. How do moles relate to volume? Okay, so when you're dealing with moles, we deal with Avogadro's law. You know this dude loved his moles, right? So when in a flexible container, if the amount in moles is increased, then the volume increases. That makes sense, right? If you put more of something in, you're going to get more of it. And if the amount of moles is decreased, the volume decreases. Well, yeah, okay. And at the same temperature and pressure, gases at the same volume contain the same number of particles. So here's our buddy Avogadro again. And it says the balloons all have the same volume, and this means they contain the same number of molecules. So Avogadro's law, not Avogadro's number, says that amount and volume are directly proportional. And that's kind of logical, right? That makes sense. So Avogadro's law calculations involve the change in volume and the amount from known starting points. And those would be V1 and N1. So here you have your known volume and your known amount. And then that gets multiplied by some constant, and you get your new volume and your new amount, right? That makes sense. So now we have Dalton's law of partial pressures. So Dalton's law of partial pressures says that the total pressure exerted by a mixture of gases is equal to the sum of the partial pressures of the gases in the mixture. And that's if the temperature and pressure are constant. So basically, guy is saying, if this is at 1, let's say this is atmosphere. It may be mercury, I don't know, but let's say it's atmosphere. If this is at 1 atmosphere and this container is at 2 atmospheres, if you put these gases together, you're going to get up 3 atmospheres. And this is the equation for that. And we won't be doing too awful much with it. Then you have Graham's diffusion or effusion law. So Graham's diffusion law says that, and this is what Graham found experimentally, the rate of diffusion of a gas is inversely proportional to the square root of the mass of its particle. Makes you wonder what this dude was up to. Like, really. So the rates of diffusion are different gases are inversely proportional to the square roots of their mass densities. So here we have a partition and in this box, and this is a good example of diffusion versus effusion. So here's a box, there's particles on one side, and we have to pretend they're just invisible particles on this side because we know there are particles there, right? It's not a vacuum. And if you pull this partition out, you get diffusion, which means they've just mixed together. Now, in this case, the partition has a little hole in it, and this is effusion. They make their way in. This hasn't been totally removed, but it's sort of like they're eking their way in through that little crack. So in this case, the rate 1 is the rate of effusion for the first gas, and that would be in volume or number of moles per unit time, because it's a rate, so it's definitely number of something over time, right? And then rate 2 is the rate of diffusion for the second gas. And M1 is the molar mass of gas 1, and then M2 is the molar mass of gas 2. And so you end up with something that looks like this. Rate 1 divided by rate 2, molar mass 2 over molar mass 1, and it would be the square root of that. So now this will look familiar from your homework or from your notes. So let's go through them. I clicked the one for you there. So this should be in your notes. This would be Avogadro's law. And this is better than the example that I just showed you because you can see here that 2 moles, 3 moles. Well, I think the picture is better. The graphic is better. So what's this one here? I'll give you a second to think. So that shows Dalton's law of partial pressures. You can see the gauges change. And then this one would be Graham's diffusion law. Now what would this one be? Pulling up increases the volume, decreases the pressure. Pushing down decreases the volume and increases the pressure. Of course, that's Boyle's law. Remember, inverse. Look at your arrows. They even gave you arrows that go up and down. There's your inverse. P1 divided by T1 is P2 divided by T2. That's your Gay-Lussac's law. Now it looks here like we've increased temperature, and that's caused an increased what? Volume. So we have Charles's law. And then here we have PV equals nRT, so that's a dead giveaway for your ideal gas law. And then this one here, you got 2 molecules of hydrogen, 1 molecule of oxygen. So this looks like whole number ratios, right? So that's Gay-Lussac's law of combining volumes. So here are some of the definitions from your notes. Yours are probably similar. So for a Newton is the SI unit derived to measure force. 1 Newton is equal to the force needed to accelerate a mass of 1 kilogram, 1 meter per second. Pressure is a force over an area, force of all gas and gas particle wall collisions divided by the area of the wall. All gases exert pressure. It is one of the fundamental measurable quantities of this phase of matter. A Pascal is the pressure or stress of 1 Newton per square meter equal to 1.000 times bar or 0.100 dynes per square meter, sorry. There's lots of ways to measure pascals. STP, we talked about, is your standard temperature and pressure. That's 0 degrees Celsius at 1 atmosphere. And your ideal gas is a term to refer to a hypothetical gas composed of molecules with that follow a few rules. The molecules don't attract or repel, and the only interaction between ideal gas molecules would be an elastic collision upon impact with each other or elastic collision with the walls of the container. And remember, the particles aren't really supposed to take up any volume. Diffusion is the movement of a substance from an area of high concentration to an area of low concentration. Diffusion happens when liquids and gases, because their particles move randomly from place to place. Diffusion is an important process for living things. It is how substances move in and out of cells, which next year we will talk a lot about. And then effusion refers to the movement of gas particles through a small hole. Graham's law states the diffusion rate of a gas is inversely proportional to the square root of the mass of its particles. I really want to know what Graham was up to, man. And then here's your partial pressure. In a mixture of gases, each constituent gas has a partial pressure, which is the notional pressure of a constituent gas if it alone occupied the entire volume of the original mixture at the same temperature. The partial pressure of a gas is a measure of thermodynamic activity of the gas's molecules. That last part makes a lot of sense, right? The pressure of a gas, partial pressure of a gas, is the measure of the thermodynamic activity of its molecules. Obviously, if its molecules are more active, it's going to take up more volume, which therefore means it's going to be exerting more pressure. So now, what your job is to go back to the assignment in Teacher Ease. Well, first watch that YouTube video that didn't play in here, I apologize. And then go back to Teacher Ease and enter one of the images that you saw, a description of one of the images that you saw into the discussion. Hopefully that works out for everybody. And I'm sorry that it's going to be a couple weeks till we're back together, but fingers crossed that it's over sooner rather than later. Okay, bye guys. Say bye, Ozzy. No. Okay, bye guys.